Welcome everyone. Today I am planning to discuss the PhD thesis of very famous physics professor and a politician of Sri Lanka, Professor Nalin De Silva. He wrote his PhD thesis in 1970, 55 years ago. And the name of the thesis is Relativistic Gravitational Effects in Astrophysics. Relativistic gravitational effects in astrophysics. It's a big subject. It doesn't really say what the thesis is all about. So we will go through it. And one thing that I want to tell you is that things that we know today, we did not know at that time. So we have to go to his mindset at that time. So before I go forward, I would explain what his thesis is all about. So by 1950s or late 50s and 1960s, people started to find some objects that are very, very bright. They're so bright, they're like 100 trillion, T, not B, trillion times the brightness of our sun. 100 trillion, just imagine an object that is 100 trillion times the brightness of our sun. And they are so bright that they could outshine 1,000 galaxies. 1,000 galaxies. They're so bright. And they're not too big. They're not very big. They are like the size of our solar system. They were called quasars. So these quasars were very, very far away. Some of them like 10 billion light years away. That means light would take 10 billion years to come to our Earth from these quasars. And that is way before our Earth was born, way before our sun was born. Those light was emitted because our sun was born 4.5 billion years ago. Our Earth was born at the same time period. And you double it, and then that's how far these objects are. And it's amazing that we could see them even with telescopes. So what is the controversy? So people calculated. So you could calculate the distance from the redshift and and then you can calculate the brightness that we see here, and then the distance, so you could calculate the real brightness of these objects. And then when you do that, it came out to be, as I said, trillion times the brightness of our sun. But then some people said they're not that bright actually. What's happening is some lensing effect happening in space. Now, if you take a lens and hold it to sunlight, you could burn a piece of paper because you could increase the intensity of sunlight using a lens. But there are no lenses in the sky, in the space to do that. But there's something called gravitational lensing effect that was found by Albert Einstein in 1920s. So what is this gravitational lensing effect means? So let's say this is the quasar, and this is us here. So we are here, let's say we are here. When the light comes from quasar to us, if there's another galaxy in between, this light would go around that galaxy due to gravitational effects, due to the curvature of space-time. It's called geodesic. So when the light goes around this other galaxy that lies in between quasar and us, the intensity of light increases. So due to these galaxies lining up between us and quasars, the intensity of these quasars are magnified 100 times or 1,000 times. So they're not really bright. They're just this happen to be a galaxy in between us and the quasar. So this is one theory. And at the same time, there's another physicist called Edwin Sculptor. He said that these quasars are real. They are bright as we see it. They are bright because they're supermassive black holes. And supermassive black holes tend to attract matter around it. And then when the matter comes near the black hole, they heat up. They heat up to such a high temperatures. And that's why we see these objects so bright. Okay, so let's take a step back. So we are seeing these objects called quasars, which are far, far away, billions of light years away. And the one camp says, yeah, they are really bright as it seems. We see it. The brightness is real. Other camp says the brightness is not real. They looks bright to us because of the gravitational lensing effect, that there's another galaxy lies in between us and the quasar, and due to the space-time curvature, that we see the intensity of this light coming from quasar magnified by 100 times or 1,000 times. So that's what the second camp said. And they said that at that time they knew about a type of galaxies called Seyfert galaxies. Now these galaxies were bright too, but not as bright as quasars. So this second camp, who did not believe the brightness of these quasars, they said that these quasars are nothing but Seyfert galaxies. They are Seyfert galaxies, and their brightness got increased because there's another galaxy lies in between the Seyfert galaxy and us. So the gravitational lensing effect happened, and the brightness increased by 1,000-folds due to the gravitational lensing effect. So we think that quasars are not really as bright as it seems. The brightness is due to the gravitational lensing effect, and they are just Seyfert galaxies. So this is the second camp said. So that's what Professor Nalin De Silva is trying to establish, see which way it's going to go. And so I'm going to go through the thesis now. And in 2.1, he talks about gravitational lensing process, basic theory of gravitational lensing, which was found by Albert Einstein himself in 1925. That's 50 years before Nalin De Silva wrote the thesis. So that's just basic theory. And 2.2, he talks about the intensification of the image due to gravitational lensing. That's also theory. Nalin De Silva has nothing to do with it, but that's established theory by 1970s. And then in 2.3, he talks about probability of finding a galaxy which gives an image of intensity I. Okay, this is his work now. 2.3 is his work. Okay, now this is the question now he's going to tackle. Okay, now we are saying, as I said, there are two camps. One camp says these quasars are really bright, as it seems, as we measure. That's what their brightness is. That's the first camp. We believe the calculation. We believe the brightness is real. And they are really 100 trillion times bright as our sun. 100 trillions of times. That's the first camp. And the second camp says they're not bright as it seems. The brightness have increased 100 folds, 1,000 folds due to another galaxy lining between us and the quasar and creating a gravitational lensing effect. They are just Seyfert galaxies. Okay, so that's the second camp. Now, what Nalin De Silva is going to do is this. He's going to say, okay, at that time there were like thousands of quasars were found. Now in 2025, we have millions of them we have found. So there are plenty of them out there. So this is the question. So if these quasars are Seyfert galaxies at far away, and we know the density of galaxies in the universe, okay, density of matter, we know, we have an idea. He used that numbers. We know the matter distribution. We could ask the probability of a galaxy sitting in between a quasar and us. So let's think about this way. Let's say you go to the forest, okay? So there are animals in the forest. Let's say open savanna, open field. There are animals, there's deer, bears, lions, whatever. So you take a bow and arrow and you shoot. And what is the chance? Let's assume all these animals are not running away. They're just at one place. And what is the chance that if you shoot blindly, that would hit an animal? So that depends on the size of the forest. I mean, if it's a huge area, then the chances of hitting an animal is very rare. A number of animals in the forest. And that's the other thing. If there are a whole lot of elephants and a whole lot of deer, then chances increase. But let's say we know the density of animals. Let's say there's a animal, some kind of animal. Let's say deer. There's a deer every 5 feet. Every 5 feet there's a deer. And then you take a bow and arrow or you take a gun and shoot. Blindly, without aiming. You blindly shoot. And then you could calculate the empty spaces in between. There's a chance of our bullet going through empty spaces versus hitting a deer. You can calculate if you know the number of deer in the forest and if you know the area of the forest, which we can calculate. It's statistical. It's statistics. It's just common sense statistics kind of thing. So that's what Nalin De Silva is doing, except that he calculates the intensity of these quasars using a physics equation. So he calculates the intensity of the quasar, and then he calculates the magnification of that intensity using, physics equation, theory of relativity equations. And then after that, he would use normal statistics and logic and see what are the chances of a galaxy line. We know the distribution of galaxies. What are the chances? What is the chance of a galaxy line between a given quasar and us? And then he concludes that chances are remote. I mean, what we observe certain amount of Seyfert galaxies. There's not enough Seyfert galaxies to account for all the quasars that we see. That's what he's concluding. That was in 1970 that he did. But today we know it's true. Quasars are not Seyfert galaxies. They're bright as it seems. But this is the problem, though. This is known to other scientists because the universe is huge. There's a lot of galaxies. There are 2 trillion galaxies in the universe. But the space between the galaxies are humongous. For instance, our nearest galaxy to us is Andromeda. That is 2 million light years away. It would take 2 million years for the light to go from here to Andromeda. And we are in a galaxy cluster called local group. But if you take the whole universe, the average distance between 2 galaxies would be 30 to 50 million light years. So even though there are a lot of galaxies, the empty space is huge. The matter density is like minus 10 to the power minus 30 or 13, something like that, kilograms per cubic meter. That's how thin the matter has spread. So there's not enough galaxies to account for all the quasars. That kind of knew, the physicist knew, but he shows with general theory of relativity and normal probabilistic logic. It's like this. Let's say somebody do elaborate calculation. Go to the forest, let's say a huge forest, and there are 5 deer. You take a gun and you close your eyes and shoot. And if the forest is like the size of 100 soccer fields and there is only 5 deer, chances of hitting a deer is very rare. Okay. So it's something like that. There's not enough galaxies to block the light coming from these quasars. Because we knew that because the universe is so huge, so vast, the distance between galaxies are so huge, chances of blocking having a galaxy in between us and a quasar is very rare. And for us to see all these thousands of quasars, it simply cannot be due to galaxies blocking those quasars. So that kind of knew because the universe is vast. But anyway, he did his calculations and he got that using some general theory of relativity equation. Like he used that for the intensification of quasars and used some common sense and statistics. And okay, so that's 2.3. And then 2.4 is the cosmological treatment of Schwarzschild metric and the Robertson-Walker metric. So let's talk about this. So when Albert Einstein came up with his field equations, you need to find something called metric to solve those equations. Metric is basically distance between 2 points. That's what it is. Metric is distance between 2 points. In a piece of paper like this, metric is Pythagoras theorem. Distance between 2 points is, let's say, z. Z is equal to x squared plus y squared square root. Z squared is equal to x squared plus y squared. So that's Pythagoras theorem applies to piece of paper. Okay, so that's good. But the space is curved. That's what Einstein said due to gravitational effects. So the x squared plus y squared equals z squared will not work in space because curvature of space. But Carl Schwarzschild, what he said was, let's say we take our sun and we could consider the space around the sun to be curved, but when you go further away from the sun, at some point there's no curvature. The universe, the curvature of the universe is zero. That's what Schwarzschild assumed. And that's what he used, the metric that he used, or this distance, or the Schwarzschild metric, using that assumption. But Robertson and Walker came up with another metric, distance between two particles, that they calculated. Okay, they kind of agree with the Schwarzschild idea that space is more curved near an object like uh, sun or earth. But when you go far away, Schwarzschild assumption was that curvature becomes zero. But the Robertson Walker curvature found a curvature for the universe, universe background, using all the matter in the universe, and they came up with a different metric. So what Nalin De Silva is doing is that he's using that second metric, Robertson Walker metric, to show the same thing. Okay, it's good work. It's good work. All right. Next one is Einstein Zeta universe. The Einstein Zeta universe is considering that the curvature of the matter density uh, of the universe somehow balances out and the curvature becomes zero. And today we know that that's not really true, because we got dark matter and dark energy, but at that time we didn't know those things. So Nalin De Silva consider those effects, and that is also, I would say, acceptable and good work. And 2.6 is where it's totally unnecessary. That's called Milne universe. Now Milne universe is basically, he assumed that there's no matter at all. If we can come up with a curvature with universe without matter, which we can, you can use Einstein's equation and find a metric. Why would Nalin De Silva consider Milne universe? Because we know that there is matter. Milne's idea was disproven at that time, or it was more mathematical exercise that Milne did. Why would someone want to check with his calculations with a universe that obviously would not exist, because we know that there is matter in this universe? So that's totally unnecessary, and I have no idea why he included that. And the De Sitter universe was a possible universe at that time, so it's okay to consider that. 2.8 is the steady state model. Now that is totally unnecessary to consider, because the steady state model was totally disproven by 1970. It was disproven by early 1960s. What is the steady state model? So when we found out, Edwin Hubble found out the universe is expanding, one group said that everything started from a very small nothing, the Big Bang group. Other group said universe is going back, oscillating, going like that. Go up, go expand, and then come back, expand and come back. That's the steady state model. But there are a lot of problems with the steady state model. If the universe was around for billions or trillions of years, what happened when a star is dead? Our sun is going to die one day, and then it would end up as a white dwarf. If a person dies, I die, or anybody dies, we get deteriorated. If you get buried, get deteriorated and go to the soil. If you get cremated, you go to the air, and there's no sign of us after 20, 30 years after you're dead. But that's not the case with stars. When a star dies, it's not deteriorating. It's going to stay there till forever. It's called white dwarfs. The big star is going to stay there. It's not deteriorating. Those are corpses of stars, dead stars. They don't deteriorate. They're there. Now, if the universe is trillions of years old, according to the steady state model, our universe would be all full of dead stars. There should not be anybody to have any space. Just imagine if we all become marble after you're dead, and it's not deteriorating. At some point, the universe is going to be full of dead marble bodies, dead bodies. And there are other issues like Big Bang theory, which came up to be true with the cosmic microwave background radiation, etc. I'm not going to go into that. All what I'm saying is that steady state model was totally disproven by 1970, and for him to consider that is totally useless exercise. And 2.9 is the comparison of all these ideas. And 3.0, so far he considered these galaxies, that the in-between galaxies, to be point masses, and he considered to be spherical mass. And then he considered non-uniform distribution of matter, because this was one of the assumptions before, and now uniform distribution of matter, and then now he's considering non-uniform distribution of matter. So that's basically the thesis. My assessment is there's a lot of physics work, there's a lot of equations, his knowledge of general theory of relativity is extremely good. But the question is, the problem that he chose is it's not that important, because his main work is in 2.3. That's his main work. Other things are, he's trying to prove that there's not enough galaxies in the universe to create the gravitational lensing effect. The universe is so huge, and the galaxies are far apart. As I said, if there's only 5 deer in a area of 5 soccer fields, I mean 1 deer for 1 soccer field, you shoot an arrow blindly, it's not going to hit a deer. Chances are remote. So physicists know that the universe is so huge, even though there are so many galaxies, chances of galaxy, quasars getting blocked every time, there are thousands of them, all of them getting blocked by galaxies, it's extremely rare. It was known. So to pick that subject to do a thesis, I don't know, it's that. And most of his real work is in 2.3, which is not much. But his knowledge of doing all the other things, like doing calculations for cosmological treatments, Schwarzschild metric, Robertson-Walker metric, and Milne universe, DC, most of them are steady state universe. Most of them are not really necessary. But he shows he had to do those things, and he had very good knowledge of general theory of relativity. So that's my assessment. He did a lot of work. He showed that he has very good knowledge of command of general theory of relativity, but the problem that he chose to tackle is not that important, and most of the work is waste of time. It's not giving us anything new, like especially Milne universe is a real, and the steady state universe. These are disproven theories. Why do you want to go back to a disproven theory and do analysis, even though it involves a lot of mathematics and etc. So, so that's my conclusion. Thanks a lot for listening.